Okay. Thanks, Mike, and let me echo your thanks to everybody involved in the organization of this. It's been a very fun and interesting few days. So since I'm kind of the other bookend of the conference, I wanted to revisit Duncan's last slide from his talk, where he talked about Goldilocks problems for computational social science and laid out some desiderata for them. Today I want to talk about I'm going to talk about a specific problem and solution to that problem in the area of privacy, of data privacy. I want to make a general pitch that I think privacy is a good topic for the merger of computer science and the social sciences to think about. It has a number of very nice properties. So one property is that social science itself needs solutions, will be a consumer of solutions for data privacy, especially insofar as it touches on social data that's about interactions between people. And I think that computational social science won't just be a consumer of solutions, it's well positioned to be a provider of solutions as well, because there are both computational and data-centric problems there. But there are also these sort of bigger issues of policy, sort of government, business, individual concerns. So this really is sort of a large-scale social problem. And if you look at the Goldilocks list that Duncan put up in his talk, I think privacy also fits the desiderata that he described. So it's clearly sort of privacy in the large is very clearly not an obvious problem with obvious solutions. I'll say a little bit more about that in a second. But I do think it's also progressive in nature. I mean, it's very early days still, but I think we're starting to see interesting, rigorous, yet practical approaches to privacy. I will talk about one such approach today. And so, the goal of having a problem where there's an easy version that yields concrete deliverables in the near term, I think is there. But on the other extreme, the hardest version is completely open in scope. It's obviously still a science problem, even though there are, I think, opportunities for both glorified consulting and clearly opinion as well in privacy. And in general, it's not creepy, although I'll leave you to judge whether the particular piece of work I'm going to talk about today has a bit of a creepy element to it. I think it might. But in general, trying to find solutions to privacy is an effort at deliberately making the world a less creepy place rather than a more creepy place. Okay? And so I think, I just wanted to, first of all, recall these goals that Duncan set out at the beginning, because I think they're good ones, and they're the ones that guided us in these ongoing discussions that led to this workshop. And let me further argue that, Duncan, he gave this great talk in which he said, look, a lot of the questions that are the oldest in the social sciences, despite 100 years of study, people don't even agree on what the problem is. And privacy is very much in this category today. This is a quote by a very well-known privacy researcher named Daniel Solove, who says, privacy is a concept in disarray. Nobody can articulate what it means. It suffers from an embarrassment of meaning. So there's sort of too many definitions. There's too many different things that people mean when they talk about privacy. And the particular piece of work I want to talk about today has a kind of interesting backstory. So last year I participated in, and perhaps was the least contributor to, a National Research Council study that was the result of a direct request from Obama's office. This was a study that was requested in the light of the post-Snowden revelations. And the question phrased to the study group was deliberately very, very narrow. The question was, are there technological alternatives, near-term technological alternatives to the bulk collection of metadata that would still allow intelligence agencies to do their work? Okay? And the result of that study was, which was a very, very interesting topic, yet somehow resulted in, this publication, which has possibly the driest title that I could possibly imagine, Bulk Collections of Signal Intelligence Technical Options. And, the answer to the question that was posed to us, you can guess what it was. I mean, you can go read this thing. It's about 100 pages long. But the summary is that no, there are not, near-term technological alternatives. And the reason really is because of the way that the NSA and other intelligence agencies use this data, which I'll talk about in a moment. One of the other interesting things about this study was, when I say that the question was very narrowly put to us, it was made very clear that we were not being asked for our views on whether the bulk collection of metadata was a good idea, was legal, was ethical, etc. It was just a bunch of scientists being asked to weigh in on this very specific question. And so I participated kind of lightly in the study. One of the things that amazed me about it is how many incredibly busy people dropped everything they were doing for several months and started appearing, every week or every other week in D.C. And so I kind of felt bad and left in the dust because I wasn't capable of doing that on such short notice. And so I didn't end up really doing much on the study, but it did kind of leave me with a very particular problem in my head. That I came back and talked to a bunch of colleagues at Penn about, most especially my faculty colleague Aaron Roth, who's one of the gurus of differential privacy. And I'm going to tell you about the problem that we kind of posed as a result of this study and the solution that we came up with. Okay? And so just to now kind of back up a little bit and frame the problem a little bit better, I ask you to consider the following hypothetical scenario. Some unnamed intelligence agency holds the interaction metadata of its citizens. So think about, records of telephone calls between individuals. Think about, social media exchanges between individuals or email exchanges. So essentially, a social network is the underlying data set. And this intelligence agency perhaps has a legitimate interest in using this network data to search for, bad actors in the network. Okay? And an important kind of consideration here is that the network itself can provide leads to finding those individuals, but actually detecting whether somebody is a bad actor is a much more expensive and a much more intrusive operation, okay? So what I mean by this is, you can kind of use the network as a gradient. If you know about one bad actor, you can posit that bad actors are more likely to communicate with each other than, non-bad actors, and sort of use the network structure to sort of prioritize who to take a harder look at. And I'll say a little bit more about this in a second. But this is essentially how the NSA uses this data. You can kind of think of it as a fishing expedition with a gradient that's given by the network structure. And so the question is, how can the hypothetical intelligence agency balance its mission with both the expense of kind of more intrusive investigations of individuals and also still provide some privacy guarantees? And my main kind of non-contribution to this study was that at a couple of points in the study, I said, it seems like ideas from differential privacy, which I'm about to describe to you, could be adapted to this problem where you essentially have a subpopulation that has no privacy rights, but you still don't want to give up on privacy in its entirety for the people that are not the focus of your investigation. And, the couple of times I mentioned this idea, it was, I think correctly at the time shot down by the other people on the committee who knew anything about differential privacy, because they said, well, differential privacy is a non-starter here because by definition it guarantees privacy for everyone, right? And, clearly terrorists should not have any expectations to privacy. Okay, and so this was sort of the kind of my state of mind when I came back from this study. And just to say a little bit more about what I'm going to mean by privacy here. By privacy here, I'm going to mean that the identification of the bad actors or whatever subsequent action that the intelligence agency takes on these bad actors shouldn't reveal very much about the data, the specific network data of any particular individual that's not actually a bad actor, for instance, a terrorist. Okay, this is kind of the idea behind differential privacy in this setting. So let me talk about differential privacy for a second. So usually the Simons Institute sponsors and holds workshops that have some very, very strong connection, not just to computer science, but to the theory of computer science. And so, at the very last second, I think I'm going to provide that link for this workshop. I don't think there's any direct references to theoretical computer science yet. So differential privacy is a theoretical model. It's a mathematical definition or framework for thinking about data privacy in a very general way. It was introduced by Cynthia Dwork and other colleagues back in 2006. statistics, and it's really kind of seen quite an explosion of research in the last decade, especially on the theory side. But we're now actually starting to see, I think, practical implementations of ideas that have come from differential privacy. And so I first want to just kind of walk you through at a high level, what the basic definition is, what the basic concept of differential privacy is, and then I'm going to talk about how to modify that definition for the specific setting where the underlying data is network data, is sort of communication data between people in a social network, and where you don't want to provide privacy guarantees for every individual in the population. Okay, so first of all, differential privacy is a definition about algorithms, right? It's a definition, an algorithm either is differentially private or it is not differentially private. So it doesn't talk about whether the data itself is private. It talks about whether an algorithm manipulating data treats that data in a particular way that has some sort of privacy guarantee. Okay? And yeah.
I mean, just to link it back to your question, so in some sense, like, why did you feel that the NSA or whatever, it's more important that the algorithm operate privately than actually just like having the data there? I mean, because obviously there's security risks.
Good. So there are many. So two comments. So there are many things that one might want in a differentially private algorithm for the problem that I'm going to describe, and we're not going to provide all of those things. So in particular, I'm kind of already starting from the point where we assume that this hypothetical agency has this data for better or worse and wants to use it for the stated purpose. And so debates about whether this data should have ever been collected in the first place or whether it's, secure, being securely treated in McLean, Virginia, I'm kind of punting on, and those are very, very important questions. More generally, differential privacy kind of also punts on the question of, what data should you be collecting in the first place? Are you kind of securing it in a proper way, or encrypting it in a way that can't be read? Its starting point is that an algorithm has data. Or you can also think of it from kind of a mechanism design point of view. An algorithm wants to incentivize a population to contribute their individual data sets to some centralized computation. And one of the factors that those individuals will think about is whether their privacy will be guaranteed.
You could possibly use these ideas to think about how to store the data differently as well, but you're just going to take this.
Yeah, and I think that that's slightly more in the realm of cryptography than it is of privacy. And by the way, it's easy to kind of confuse those two things, but at a high level, I think, cryptography is very much about a computation not revealing more than the result of the computation itself. Okay? Whereas I think privacy is much more about what does that computation actually reveal. Okay? And so both of them are very important, and both of them have application to privacy. But I think of kind of data storage, sort of secure data storage, as being more of a crypto problem. And this is more about like, well, I'm going to perform a computation and release the results of it. What information about individual citizens is leaked by that publication? But these are all very, very good questions, and I'll try to be, somewhat clear within the confines of not getting too technical about kind of what aspects of the problem we're addressing and which ones we're not. Okay, but so what is differential privacy? So we say that an algorithm A is differentially private. So imagine an algorithm that takes as input a database, if you like, or a vector, right? And so I'm going to call that vector D here for a data set. And think of that data set as consisting of a bunch of individual data sets of the particular members of a population. So DI here is the data set of person I. So if you want to think concretely, D of I might be the phone calls that you've made in the past year. It might be, who your contacts are in some broader social network, et cetera. It might be your medical record in a medical application. But think of D sub I sort of being your data set that you care about protecting in a private, having some privacy guarantees about. And so in differential privacy, we think about the algorithm as taking this aggregate data set for an entire population. And the property we want, and I'll put up the next line in a second, but I'll just say it in English first. The high-level idea of differential privacy is if you go into any data, if you take any data set, and you kind of modify just one component of it. So I go in and I change only your data. And in particular, think about the change where I delete your data. So we're sort of comparing the computation that would be performed with your data present or without your data present. I basically want the outcome of the computation to be only negligibly altered by the omission of your data set, for instance. And so the way we formalize this is that we say that an algorithm, a randomized algorithm, you'll see that the definition I'm about to give requires, it's sort of a fundamental component of differential privacy that we have randomized algorithms. A randomized algorithm is differentially private if for any data set D, any neighboring data set D prime, and by neighboring I mean this sort of counterfactual Nash equilibrium type, go in and just modify the data of one individual in the vector, we essentially have that the distribution induced over outputs is almost identical. Okay, so think of this randomized algorithm for any fixed data set. Because it's a randomized algorithm, even for a fixed data set, its output will be randomized. Okay, there'll be some distribution over possible outputs of the algorithm, and I want that when I compare that distribution with the distribution induced by changing one element of the data set, that those two distributions are kind of controllably close. So, one way of phrasing this is for any possible thing that the algorithm could output, we want that the probability that the output of the algorithm is that particular output O when the input is D versus the neighboring data set D prime is approximately the same. Okay, so to demystify this a little bit, think about the example where the input data set are the salaries of people in a large company. And let's say that every week the company wants on Friday to publish the average salary of the employees in the company. Okay, so the natural thing for so one thing that the company could do is actually every week take everybody's salary, compute the average, and publish it to numerical precision. Sort of show all of the decimal values in the average salary. And this would not be a differentially private algorithm, right? And the reason at a high level it's not private is that if the only thing that happened between last Friday and this Friday is one person joined the company, okay, then by looking at the salaries on the two successive Fridays, we can back out the precise salary of the new employee, okay? So the differentially private solution to this is mercifully simple. You compute the average salary and then you add some noise to it. Okay, and at a high level, what you'd like is that the amount of noise you have to add sort of scales nicely compared to the size of the population. And so it's pretty easy to see just from sort of basic probability theory that in this case, that if I add noise, which is kind of on the order of 1 over the square root of the number of employees, I will still have a numerically pretty accurate estimate of the average salary, but you couldn't back out any individual salary from that number or even from successive noisy estimates of it, okay, on two successive Fridays, okay? So that's the idea of differential privacy. Your algorithm is going to be a randomized algorithm that outputs, in the example I gave, it was a single number, but it could be, a vector of numbers. It could be a much more complicated output. A good example would be, I would like, I'm a medical researcher. I want to invite people to give me access to their medical records. I'm going to, try to build a predictive model, let's say using least squares regression to predict the probability of a disease given a bunch of symptoms and test results. And one thing I could do is publish the actual coefficients of that regression to numerical precision. And the kind of question that differential privacy is designed to ask and answer is it okay to do that? I mean, it kind of seems like, well, what information about any specific person's medical record could be compromised by releasing the coefficients of this aggregate, least squares computation, but the average salary example should show that you should be worried about this, okay? And so in differential privacy, you have a randomized algorithm, whatever space it outputs from, we'd like that the distribution over outputs is negligibly modified by a small change in the underlying data set. And, so here's just a cartoon of this. This is a cartoon in the case where the underlying data set is a social network. And, here I've got the original social network, and here I've got a modified social network where I've just added one edge between two individuals. And what we want from the differentially private algorithm is if this is kind of a cartoon of the output distribution, that the two distributions under these nearby inputs are also very close to each other. Yeah?
Quantify this change in the distribution using some sort of...
Yeah, good. So that's the next line. So the more precise version of this definition is that we say that the algorithm is epsilon differentially private for some small epsilon if the probability of any particular output changes by at most a multiplicative factor of like 1 plus or minus epsilon, okay? And so that's a parameter of the algorithm, right? So one of the nice things about differential privacy, and I'll say a little bit more about this later, vis-a-vis that, one of the problems with debates about privacy, and I very much experienced this on this study, is that it's kind of like political discourse in the United States right now, right? You just have there's sort of one camp that, especially on topics of things like terrorism or let's say, fighting infectious diseases, epidemiology, there's sort of one camp that says these missions or this, sort of the societal importance of counterterrorism is just so overwhelming that it should, trump any notion of individual privacy whatsoever, okay? That's one viewpoint. And then there's another viewpoint that says, no, I don't care what threats we're subject to. Individual privacy should trump everything. And of course, if these are the only two choices, we'll never get anywhere, right? And so I think one of the big problems in privacy is just creating a language and solutions that give choices in between these two extremes, right? And so one way of giving a choice is by basically having this parameter that says how private the algorithm is, okay? And of course, that has to be traded off versus the utility of the algorithm, which I'll talk about in a second, which is sort of how good how useful the output is. Okay. Okay. So does everybody understand the basic notion? Yeah.
So in your example with the salaries, the question is, could we identify the salary of one person?
Right.
So the answer there is yes or no. So there's some epsilon for which the answer is yes, and there's some.
No, it's more that, okay, so if you're an individual in this computation, right, here's sort of the guarantee that you're given. And let me say a little bit more about this, right? So, so the fundamental nature of this definition is that the inclusion or exclusion of your data from the computation doesn't change the output of the computation very much. This doesn't guarantee that bad things won't happen, just that whether your data was included in the computation or not doesn't matter much, okay? So if there's some set of outputs, if the output of the algorithm falls in some particular set that you're worried about, you don't want, the computation to result in that particular output or set of outputs, this definition isn't saying like, well, I'm promising you that bad thing won't happen to you. I'm just saying, for instance, if epsilon is 1, for instance, I'm telling you that the probability of that bad thing happening won't change by more than a factor of 2 by you including your data in the computation. And I particularly choose that value because, in general, hopefully the bad event that you're worried about has a small probability, and so a factor of 2 is not a big deal, right? So if it was kind of extremely unlikely that this bad thing happened to you without your giving the data, then it's only twice as likely to happen by your giving the data, okay? And so that's how it's quantified, is in this epsilon, okay? So it doesn't guarantee, and this is, I think, another high-level point I'd like to make. Be suspicious of any definition of privacy that guarantees that, bad things can't happen. You should be suspicious of any such definition, but one that doesn't guarantee that, but just says, sort of quantifies how much worse off you could be by participating in the computation, is a sort of sensible alternative. Okay. Okay, so let me just, so now that I've given at least the flavor of the definition, let me just make a couple of high-level observations and point out some nice facts that are known about differential privacy. So first of all, observation number 1, differential privacy is easy to obtain trivially. You could just ignore the input, right? So if I just don't pay attention to the input data and output like a random number, this will satisfy differential privacy, okay? Because no matter what data set you give it as input, it's inducing the exact same meaningless, completely information-free distribution over the output. And so the point of this observation is that the real trade-off here is between privacy and utility. So the utility part is not part of the definition of differential privacy. It's just talking about the privacy guarantee. But the goal of the research in differential privacy is to pick up different types of computations and say, there's a way of doing this algorithm, there's a way of doing this computation in a way that on the one hand promises differential privacy and also promises some utility results. So in the case, for instance, of regression, for instance, the goal would be to give a linear regression algorithm that guaranteed differential privacy, but for which you could also prove that the out-of-sample error of the resulting model was almost as good as what you would have gotten on the same data set ignoring privacy. So the kind of gold standard is to kind of take the best algorithm that you know for doing the computation in a non-private way and to kind of get an algorithm that's almost as good with respect to what you care about in that problem while still providing a privacy guarantee. And one of the, I think, when I first saw the definition of differential privacy, I'm relatively late to working on differential privacy. The first time I saw it, my reaction was like, wow, that's the right definition of privacy, in the sense that if you could achieve that, it would be great. It would be a very, very strong natural guarantee. And of course, the first concern with such a definition is that maybe you won't be able to do anything with it. Maybe you'll never be able to get, nothing will meet the definition. You won't be able to find differentially private algorithms for interesting computations. Luckily, it's turned out that pretty much the opposite is true. So many, many common, important, fundamental types of computation can be done in a differentially private way. You need a different algorithm than the classical algorithm, but there is a way of doing it differentially private. So, for instance, much or even most of what we're familiar with in machine learning and statistics have a differentially private version. So this includes things like, least squared regression and many other types of machine learning tools, linear programming. There's a differentially private version of linear programming, of convex optimization more generally, and the list is kind of growing as time goes on. Differential privacy also has very nice kind of programming properties. So one of them is composition. So if I have two differentially private algorithms, A and B, and I give the output of A to algorithm B, so I'm chaining together two differentially private algorithms, the resulting composition is also differentially private, and the sort of degradation of privacy scales only linearly. So if I had an epsilon differentially private and a private algorithm and an epsilon prime differentially private algorithm, then their composition is epsilon plus epsilon prime differentially private. Okay. It also is robust to post-processing. So this is kind of like, if those of you who know the data processing inequality information theory, which sort of says that you can't create new information by subsequent computation. Differential privacy has a similar property. So if I give you a differentially private computation and you take its output, no amount of subsequent computation on that output, including computations that combine that output with other unforeseen data sets, can eradicate the original privacy guarantee. So this is extremely important, since these days a lot of privacy breaches happen because of essentially triangulation of data sets, right? Sort of, party A releases some apparently anonymized database, party B releases some apparently anonymized database. By combining them together, you're able to back out, the data sets of specific individuals in the population, okay? So sort of by its nature, differential privacy prevents kind of attacks like this, okay? And at a high level, the way one gets differential privacy is kind of like the way I described the average salary example. You add noise to your computations. Sometimes to get the best result, or even to get the result at all, that noise needs to be carefully structured or correlated. So there's, kind of some cleverness required in the design of the algorithms. But at a high level, what you're doing is adding noise to computations at different stages in a way that allows you to get the privacy guarantee. Okay, so that's the basic definition of differential privacy, and to kind of modify it for the problem that was inspired by this NRC study, we need to kind of do two things. One is kind of adapt the definition specifically to the setting where the underlying data is a network, meaning your data is sort of who your phone calls have been to or who your friends are on Facebook, for example. And so, and then we also want to kind of model this fact that some individuals in the population have no privacy guarantees, but the other ones should have a privacy guarantee. And so let me just, I'm not going to get very technical. You can look at the paper for the details. But at a high level, right, the private data of an individual, the kind of D sub I that I was talking about before, are their edges in the network, in a large-scale social network. I'm assuming that the intelligence agency is already in possession of this entire network in a centralized way, for better or worse. And then to model this idea that some parties in the population have no rights to privacy, I'm going to do this in a very abstract way, which has both advantages and disadvantages. But the abstract way I'm going to do is I'm going to assume that each individual in the population or each vertex in the network has a hidden status bit. Okay, and that hidden status bit basically is just a 1 if they're kind of a target of the investigation. They're a terrorist, for instance, and it's a 0 otherwise. Okay, and my assumption is that the algorithm that's doing this kind of network search on this graph is able to investigate the status bit of any person in the population, but that it's an expensive operation, right? So think of that as sort of an operation you want to minimize. So think that, and I think this is very much models the way things actually are at the NSA from what I learned on this study, which is that, the data itself is there, cycles are cheap, so sort of doing anything they want on the graph itself is something that just involves kind of computer time. But actually deciding to really figure out whether some individual is perhaps engaged in terrorist activity, that's a very, personnel intensive and expensive operation, because it either means, it can mean anything from putting people under surveillance to doing more extensive background checks on their travel, on their financial records, et cetera. And that's not, that's sort of analyst time. That's not CPU time, okay? And so what we want are algorithms for the intelligence agency to efficiently discover kind of vertices with a status bit that's 1, but in a way that provides differential privacy for everybody whose status bit is a 0. Okay, that's kind of the high-level algorithmic problem that we're trying to solve here. Okay, I don't have time to give kind of a detailed example, but you might be wondering, like, well, what could go wrong with the standard thing? So what's the standard thing? So the standard thing is what they call in intelligence circles contact chaining, and that you might think of as fishing expedition using a social network, right? So what they do is they start with some individual or individuals that are kind of seeds that they know are, are bad actors. Okay, they know that they're involved in terrorist activity of one kind or another, and what they use the social network for is they do kind of a breadth-first search, right? They sort of say, well, let's see who this person calls a lot, and then they go to those neighbors in the network, right? And they say, let's look at their status bit. Let's do a bit of an investigation. And so they might see, okay, this person that gets called all the time is, the pizza delivery place around the corner from this bad actor, and so no need to do any further investigation there. And then somebody else they find, might actually be another suspicious individual. And so they'll sort of grow a connected component of targeted individuals, okay? And this part actually doesn't present any problem for privacy, right? Because if all you do is sort of grow a connected component of targeted individuals, even though you will have looked at the status bit of innocent or non-targeted individuals along the way, if all you do is publish or act on the connected component that you found, it's not hard to convince yourself that this actually will obey differential privacy even without any randomization. The hard part is when you want to jump to a new component. And the best kind of high-level example I can give of this is a little bit abstract, but many of you have probably seen movies in which there are sort of two organized crime groups, right, that are, there are two cells of an organized crime group, and there's sort of only one contact person who, is the communication path between these two connected components of maybe mafia members. And it happens to be that person who's the bridge between these two groups is an informant. okay, for the authorities, right? And the worry is that if you kind of use that bridge to find the second connected component and then act on that second connected component, it might compromise the privacy of the bridge. Okay, and in this case, that's your informant, and you don't want to do that, right? So you have to be very careful about jumping from one connected component to another. And this is sort of where randomization is required. Okay, and so I'm not going to describe the algorithm in detail, but I'm just going to describe to you at a high level, what the modification is that gives you differential privacy, and say a little bit about performance on my last slide. So. Think about, what we actually do in the paper is kind of give a general transformation of a certain class of non-private algorithms into algorithms that are private. So think of that class of algorithms as being more or less what I've described here. They're algorithms that start off with one or more seed individuals that then do some sort of local breadth-first search to find a connected component of targeted individuals. And then, the kind of the assumption we make in the paper, the sort of very general abstract assumption that we make, is that the search for, once you find a connected component, the way that you find your next component is through what we call a statistic of proximity. So what's a statistic of proximity? A statistic of proximity is just sort of a graph theoretic metric that tells you, given a set of individuals in the graph, given a set of vertices, think of that as like the component that I've already found, and given any other vertex in the network, what's the distance from this vertex to this set of individuals, okay? So there are many, many reasonable definitions for this in the graph theory literature. So the most common one would be, if you give me a set of vertices and another vertex, the distance from this vertex to the set is the shortest path distance from this vertex to any individual in the set. Okay, that turns out to not be such a great choice for a reason I'll describe in a second, but you can do it. A different one would be, what's the number of common neighbors between this individual and this set? Okay, so instead of looking at shortest path distance, I'm looking at intersection of neighbor sets. Okay, but either think of these two examples of statistics of proximity, and think about algorithms that when they want to find a new component, when they want to sort of start a new search from a different location in the network, think of what they do as just kind of rank ordering all of the unexplored vertices in the graph by their proximity to the terrorists that you found so far, and then sort of systematically investigating, sort of checking the status bit of each one of those individuals until you find a new terrorist, and then you kind of do another round of breadth-first search from that new individual. Okay, so that's sort of a very practical, broad class of heuristics for doing search in social networks for a targeted subpopulation that doesn't make any mention of privacy whatsoever and doesn't really have any privacy guarantees that can be made for it. And all we do in the paper is just propose that, when you're doing that jump from one component to another and you've kind of ranked everybody by their distance to the terrorists you've already found, just take the numerical values of those distances and add a little bit of noise to every one of them. Okay, and so the nice property that this is going to have by sort of taking the number of neighbors that everybody has in common with the terrorists you found so far and adding a little bit of noise to it, you're taking this ordered list and you're not completely reshuffling it, right? But you're locally reshuffling it. You're not going to take the person that was closest to the group you've found so far and swap them with the person farthest away, but you will do a lot of local reshuffling in this list, okay? And it turns out that that's enough to prove a differential privacy guarantee for all of the kind of non-terrorists in your population, okay? Does it make sense at a high level? Okay. So that's kind of the theory part of the paper. And then the utility part, to prove a utility part, just to be clear, you'd have to make some assumption about the relationship between this network proximity metric that I just described and the probability that somebody actually is a terrorist or not, right? The whole point of using the graph to guide the search is the belief that in some graph theoretic sense, terrorists tend to be closer to each other than non-terrorists. Yeah, Susan.
I'm just wondering, how to think about the set of adversaries that could be sort of trying to violate privacy. So like one of your motivating examples is like revealing an informant or something. So like, for instance, like suppose you had a mole, or you know, who like a contractor who was being able to do these kinds of queries, and so, you know, the way we're doing it on our end is we're going to find people and then sort of audit them. And so you don't have to like fully reveal people, but just like even kind of getting some information.
So think about the computation, you know, kind of without loss of generality, you can think of the output of the computation that I'm describing as a list of identified terrorists. Yeah. Okay, that's the output. And think of the adversary, if you like, as being a party that's going to take that output and with kind of unlimited computational resources, try to figure out who your contacts in the network are. And basically the adversary will have succeeded if they can infer kind of, you know, anything about your social contacts that they couldn't have inferred without the results of this computation. So it's sort of, you know, the adversary can kind of do anything that they want, and their goal is to try to figure out, you know, just one phone call that you made, right, from seeing the list of terrorists that were output.
I guess what I was trying to think about is like, and I mean, I know, I think I understand like the narrow part of the theory. I was just trying to think about like where some of the limits of the theory about like if they were bringing in some other information, or you know, using it in conjunction with something else.
Right, and so this is sort of where this kind of multiplicative guarantee. So you know, if you think of the goal of the adversary as being trying to figure out who you've called from seeing who the identified terrorists are, you know, what the definition is saying is that their ability to do that won't have been increased much by seeing the results of this computation. Now, here's a bad thing that could later happen after this computation. Your phone records just get released in a public, you know, somebody posts your phone calls on the internet, okay? Okay, so then your phone calls would definitely be revealed. All this definition is saying is that this computation is kind of not at all at fault for that, right? So the bad thing could still happen to you later for some completely orthogonal reason, but what can't happen, you know, here's what can't happen. It can't be that some later data set from which your phone records could not have been inferred can now be inferred when combined with the output of this computation. That's what's explicitly forbidden by this definition. Yeah.
A little worried about your informant. If they're the only bridge between these two cells, won't those cells kind of infer that, you know?
Okay, good. Okay, so this is a very good point. And so, so in that example, right, sort of, if that's your okay, so let me get back to these two examples I gave of what your network metric is. One is shortest path distance, and one is number of common neighbors, okay? So, you know, one thing I should have said much earlier is that you can't expect to do a differentially computation. You can't expect to do a useful or accurate differentially private computation if the underlying function that you're trying to compute is fundamentally very sensitive to one of its inputs. Okay, so you know, if the thing I want to compute is the CEO's salary, right? Then there's just no way I can kind of output a good approximation to that without revealing a lot about the CEO's salary. I kind of either have to just, you know, add so much noise to it that you have no idea what the salary is, or I have to basically tell you something about the CEO's salary. So, you know, in all differential privacy, you need to start with something which is kind of a low sensitivity function. That's a necessary but not sufficient condition. So, and that's why I gave these two different examples of statistical proximity. So if you think about shortest path distance, that's an extremely sensitive statistic because I can basically take a graph which consists of these two components connected by, let's say, just a chain of individuals. If I kind of remove, you know, and so there's some short path between these two cells, right? But if I remove one of the individuals on the chain, I just change one person's data, now the distance between these two becomes infinite. Okay, and so if I use that as my statistical proximity, you know, we still have a theorem, but you'll have to add a lot of noise to counter the fact that you have a very high sensitivity distance metric. Whereas if you use something like number of common neighbors, you can show a much nicer, a much tighter bound on the sensitivity, and you don't have to add nearly as much noise. Yeah.
Just to follow up on this line of questioning about the concept of differential privacy. So The idea of differential privacy seems to be basically that if you perturb the data set in one entry, I won't be able to tell the difference from the output.
That's right.
But I mean, if the distribution of the incoming data is such that, either I include, say, your information data set, or I drop both you and all other professors of machine learning, right? Then that means that sort of the perturbations that an adversary would actually have to reason about would be much larger, right? Because they'd be correlated across entries of the data set. And then they might easily be able to test based on the output which of these possible worlds they're actually in.
So just to be clear, right, the probability in the definition of differential privacy is entirely over the internal randomization of the algorithm, right? So the guarantee has to hold for any fixed data set as input, right?
But I mean, yeah, I guess what I'm saying is that there's a kind of, in order for it to be useful, it seems like there's an underlying assumption that the perturbations that could actually happen to the data set, like if I'm an adversary trying to reason about what the underlying data set is, if I know something about the data generating process, right, which typically an adversary is going to know something, right, there's going to be some correlations in the incoming data or whatever, I might be able to get a better test than the...
So so it is true, right, that the kind of the amount of noise you have to add is proportional to the size of the perturbation. So if you kind of, instead of doing the thought experiment about one person withholding their data, you think about some fraction of the population withholding their data, you can still chain together the definition many times, right, and move from sort of, from D to D prime, D to D prime to D double prime, et cetera, and get this sort of resulting degradation of probability. But even if there's a probabilistic model over the generation of the data, that's before we even get to the definition of differential privacy. Now that's just some fixed data set, right? And I'm still going to give the privacy guarantee with respect to that fixed data set.
We need to finish up and let Michael get done, and we can then bring.
Yeah, we can take it offline.
Couple more minutes, Michael.
Okay, good. So anyway, I was talking about, well, if you really wanted to prove not just a privacy guarantee for such an algorithm, but a utility guarantee, you'd obviously have to make some kind of mathematical assumption that relates whatever your chosen statistic of proximity is in the network to the probability of being a terrorist, right? You'd need to sort of say, like, well, people that are closer in whatever your metric is to the known set of terrorists are more likely to be terrorists than people who are far away, okay? And so we didn't bother to do that. There are some subtleties to that, but I think it's kind of a fairly straightforward exercise. But we did do some kind of large-scale experiments. And so let me just call your attention to sort of the blue and red here. So we took two large publicly available social network data sets. One is the DLBP database of mathematical collaboration co-authorship networks. The other is the IMDb kind of movie database where the individuals are actors or producers or directors or the like, and there's an edge between pairs of individuals that have been in a movie rather than co-authored a paper together. So these give us nice natural social network structures, large-scale social network structures. Of course, they don't tell us who the terrorists are, and so we actually and we thought about using kind of natural subsets. So for in our earliest experiments, we used DLBP, and we decided that the identified the terrorist subgroup that we're looking for is anybody who's ever written a paper in COLT, which is the machine learning theory conference. But we wanted to actually be able to control the component structure. And by the way, for those of you who know that community, you can think about who the Osama bin Laden of the COLT community is. Manfred Warmoth was right up there towards the top. But because sort of the crucial issue here is sort of the discovery of new components, we wanted to be able to run experiments in which we controlled that component structure more. So where we could kind of say, well, let's create a subgroup of targeted individuals that's sort of mainly one large connected component and a bunch of smaller fragments. to intermediate cases where it's a few large components to cases where it's a very, very fragmented community, right? And basically those are increasingly difficult problems, even ignoring the issue of privacy, right? If all of your terrorists are in one connected component, then once you've found one of them, you've kind of found all of them. If they're highly fragmented into tiny non-communicating cells that are really spread out, then it's just a difficult search problem, even ignoring privacy. And so we wanted to control that. And so, maybe I'll just focus on the right column here and on the red plots, which have error bars, and the blue plots, which do not. The blue plots are basically a non-private algorithm using this kind of number of common neighbors metric. The x-axis here is, kind of how many vertices have you visited and done a background check on them. You've checked their status bit. So that's kind of cost is going on the x-axis, and the y-axis is how many targeted individuals has the algorithm found so far. So the blue curve is the non-private algorithm in these three different regimes of kind of mainly one large connected component of targeted individuals, a moderate number of medium-sized components, and a highly fragmented community. You can see the y-axis changes here and gets smaller, right? Because it's just harder to find the individuals when they're highly fragmented. And the main point of this diagram is that the red curve, which is the average of our private version of the same algorithm over several hundred trials, with 95% confidence intervals around it, is quite closely tracking the blue in all three of these regimes, right? So in sort of the easiest problems, it's doing just as well as the non-private version of the algorithm in terms of its utility. In the sort of medium regime, it's tracking quite well with a little bit of lag, at different points, but still quite competitive with the non-private algorithm. And here it's doing a little worse, but both algorithms are finding so few targeted individuals at all that it doesn't really matter. Okay, so this is just some empirical validation. The green line is on one of these things where I'm using two different y-axes. The green axis is essentially showing you your risk multiplier. So as time goes on and you run the algorithm further, your privacy degradation increases. But what this is basically showing you is how much it's essentially showing you what the value of 1 plus epsilon was in the original definition. So this, for instance, is saying that at no point in this computation are you more than twice as likely to suffer some bad outcome, whatever your definition of bad outcome is, by participating in this computation versus not participating in this computation. Not that you really have a choice in the case of the NSA running an algorithm on your metadata, but if they wanted to provide some privacy guarantees, they would be able to do so. Okay, so let me stop here and let me just make maybe one more general comment that I think is also kind of a good topic for this community and this workshop to think about, which is people have cared about data privacy for a very long time, and lots of large companies and organizations that we know about, care about privacy at some level. And my impression of what goes on in these large companies these days is still that, you still have these situations, let's say at Facebook or Google, where you have armies of machine learning PhDs building predictive models from, individual data that's aggregated, and using, the results of those modeling exercises in very visible ways, right? Sort of like, what kind of search results you see, what sorts of ads you see, so on and so forth. And my understanding from talking to people in these organizations is that, it's not that they don't care about privacy, but privacy isn't their job, right? And it's not the job of the algorithm. Instead, there's some separate privacy advocacy group, perhaps within the company, that occasionally kind of, looks at what's going on in these groups, probably doesn't understand much about it, but they're kind of separate functions, okay? And differential privacy is kind of an effort to endogenize this kind of, so far exogenous, policy, moral, ethical, legal consideration in the algorithm itself. Okay, and I think that this is a major growth area in computer science and in computational science and even more broadly. And so, for instance, one thing that a bunch of us at Penn have started thinking about is what would it mean for a machine learning algorithm to be fair, for instance, instead of private? So instead of trying to sort of provide some privacy guarantee, I want to provide a fairness guarantee. So for instance, I'd like to sort of say that if I'm using machine learning to build a model to decide who to give a mortgage to based on a bunch of, characteristics I know about individuals, I don't want it to just be the case that the final model actually doesn't discriminate against any member of the population. I want that to happen even during the learning process, right? So before I kind of even know what the truth is, while I'm trying to arrive at it by learning, I'd like to provide some kind of anti-discrimination guarantee in the learning process itself. And this is another example. And I think that we're starting, I think all these things like, workers complaining about one thing that's great about Uber is that their drivers compared to taxi drivers are they like to talk a lot about their job. And so, one thing I've learned, like surge pricing, for instance, you might think that surge pricing would generally be liked by Uber drivers. The ones I've talked to generally say that they don't like it because it's kind of yanking them around, right? It's sort of encouraging them to drive to some place that they're not, and often by the time that they get there, the surge pricing has ended and they've kind of not picked up a ride in between, and now it's back to regular pricing, okay? So, of course, there's no actual evil going on here at Uber. They've just got some optimization process, but it's not the case that in that optimization process they're explicitly thinking about how their workers are treated. And I think that more and more as time goes on, there will be pressure on us as a community to try to endogenize a lot of these political, moral, legal, ethical considerations into algorithms themselves instead of having some separate advocacy group that worries about it as humans. Stop there.